Every time your streaming service recommends a film, or an autopilot adjusts an aircraft's route, you're seeing an echo. The final result of the language we were taught to hate, because we were never told that each equation was the solution to a human drama, a war of egos, the dream of predicting the future, the audacity to question Euclid himself. This isn't a maths lesson. This is the story of the secret code that built the modern world. Remember this feeling, the anxiety, the frustration, the sensation that your brain simply wasn't made for this, the silent question echoing in your mind. What's the point of this? You weren't alone. This mathematical anxiety isn't your fault. It's a documented psychological phenomenon, a feeling of dread so real that neuroscientists have observed that the mere anticipation of a mathematical problem can activate the same brain regions that register physical pain. Millions of us went through this same intellectual crime scene. We were taught that mathematics was a series of rules, a maze of procedures, a cold and soulless language focused on mechanical memorization rather than conceptual understanding. But what if I told you we were deceived? Not by a deliberate lie, but by the greatest omission in the history of education. What if I told you that behind the dryness of formulas lies a saga of rivalry, genius, and human drama as intense as any series you've ever binged? Modern educational research confirms this. Integrating history into mathematics gives it a human face, increases motivation, and reveals that great ideas were often the result of centuries of heated controversy. Prepare yourself, because you're about to discover how the mathematics they made you hate is, in fact, the secret code that built the modern world. And the story is far more spectacular than you were ever told. Our story begins with an obsession with perfection. For the ancient Greeks, like Euclid, mathematics was the language of the gods, a realm of pure forms, of eternal truths, achieved not through observation of the imperfect world, but through pure logical deduction. His masterpiece, The Elements, became the instruction manual of Western thought, the most influential book in history, surpassed only by the Bible. With over 1,000 printed editions since 1482, it was the work that taught the West to think, to build irrefutable arguments from axioms. His axiomatic method influenced everyone, from Copernicus and Galileo to Newton, and even Abraham Lincoln, who studied the elements as an adult to improve his capacity for logical argument. It was beautiful, it was powerful, but it was static. Greek mathematics was a sublime photograph of eternity. But the universe doesn't pose for portraits. It dances. And the Greeks had immense difficulty dealing with the concepts of infinity, and especially change. The infinite, or apeiron, was seen as chaotic, indefinite, a source of paradoxes to be avoided. This aversion was cemented by a profound philosophical crisis, the discovery of irrational numbers. When the Pythagoreans, who believed the universe was governed by whole numbers and their fractions, discovered that the diagonal of a simple square with side 1 was the square root of 2, a number whose decimal expansion is infinite and never repeats. This shook their worldview. Their solution: sweep the problem under the carpet of geometry, representing root 2 not as a number, but as the immutable length of a line segment. This decision, whilst ingenious, trapped mathematics. Without a way to tame infinity, it was impossible to describe the continuous flow of time and motion. Geniuses like Archimedes pushed this mathematics to its absolute limit. He was an engineer before engineering existed, a master of applied geometry, who, to the amazement of his contemporaries, used his knowledge to create legendary war machines. Accounts describe Archimedes' claw, a colossal crane that could lift Roman ships out of the water, and they tell how he single-handedly moved a fully loaded warship, using only a complex system of pulleys. But even he was limited by the tools he had. With his method of exhaustion, he grazed the limits of calculus, measuring curved areas and volumes through infinite approximations, but always formulated to avoid the direct use of infinity to maintain Greek rigor. Greek mathematics could perfectly describe what a lever was in equilibrium, but had immense difficulty describing what it became when in motion. It lacked the most crucial tool for describing reality, the language of change. For over 1,000 years, the problem of change remained a puzzle. How to calculate the velocity of a planet accelerating in its orbit. How to find the exact slope of a curve at a specific point. How to measure the area of an irregular shape. The universe was in constant flux, but mathematics remained trapped in time, frozen in the static perfection of geometry. Until, in one of the most extraordinary cases of simultaneous discovery in history, two of humanity's greatest minds, Isaac Newton and Gottfried Leibniz, independently invented the solution: calculus. Calculus was the tool that finally gave voice to motion, tamed infinity, allowing us to look at an instant of time so small it approached zero and thus described continuous change. But this invention wasn't a moment of peaceful collaboration. It was the beginning of one of the most bitter and venomous intellectual disputes in history. On one side, we had Isaac Newton, a reclusive man, intensely paranoid, who saw mathematics as a tool for deciphering the mind of God. For him, calculus, or his method of fluxions, was a way to describe physical reality. Variables flowed with time, like a river, and he was merely measuring its current. His notation with dots over variables reflected this vision of movement. On the other side, Gottfried Leibniz, a philosopher, diplomat, and optimist, who dreamed of a universal language of reason, a characteristica universalis that could resolve all human disputes through logic. For him, calculus, with its elegant notation of dx and dy that we use today, was an abstract logical system, a tool of thought, of which physics was just one of many applications. His notation was so superior that it survived, whilst Newton's became a historical curiosity. What followed was a war of egos, of nationalism, that divided the European scientific community for nearly a century, and ironically delayed mathematical progress in Britain itself for generations. The Royal Society of London, presided over by Newton himself, formed a committee to investigate plagiarism accusations against Leibniz. The committee, composed almost exclusively of Newton supporters, produced a report, the Commercium Epistolicum, which was a unilateral and unjust condemnation, tarnishing Leibniz's reputation. Continental Europe defended Leibniz and adopted his superior notation. Who invented it first? The truth is that both did from different perspectives, but the dispute shows us something profound. Science isn't a cold and objective march. It's a human passion with all its glory and pettiness. And in the midst of this war was born the language that would allow humanity centuries later to send rockets to the moon and create artificial intelligence. With calculus in hand, a new generation of mathematicians began building the unthinkable. They were the architects of the invisible, geniuses whose names are rarely mentioned outside academic circles, but whose ideas are the foundations of our world. Leonhard Euler, perhaps the most prolific mathematician of all time, was a force of nature. With over 900 books and articles, he took calculus and transformed it into a cohesive system, introducing the notation we use today: f of x for a function, e for the base of logarithms, and I for the imaginary unit. His famous identity, e to the power of I pi plus 1 equals 0, is considered the most beautiful equation in mathematics, a jewel that connects the 5 most important constants in mathematics. But this jewel is a special case of his more general formula, known as Euler's formula, which is the backbone of signal processing in electrical engineering and quantum physics. His equations also govern everything from airflow over an aircraft wing to the electrical circuits in your mobile phone. And he did all this whilst facing personal tragedy. The loss of sight, first in one eye, then the other. Even completely blind, his productivity didn't diminish. He continued dictating his discoveries to his children, a testament to the power of the human mind. Carl Friedrich Gauss, the prince of mathematicians, was a prodigy from humble social class whose genius was recognized from childhood. When, at age 7, he astounded his teacher by instantly summing the numbers from 1 to 100. He dared to question Euclid himself. He developed the mathematics of curved geometries, an idea so bizarre and useless in his time that he barely published it, fearing what he called the clamor of the Boeotians. The ridicule of the philosophical and mathematical community dominated by followers of Kant, who considered Euclidean geometry an absolute and unquestionable truth. He even tested his idea, measuring the angles of a triangle formed by 3 mountain peaks to see if they summed to exactly 180 degrees. A century later, this same geometry became the exact language Albert Einstein needed to describe how gravity curves the fabric of space-time in his theory of general relativity. Gauss's famous bell curve, which describes the normal distribution, is today the foundation of statistics, data science, and machine learning algorithms that decide what you see on social media. And Pierre-Simon Laplace, who dreamed of a universe so predictable that if an intelligence, later dubbed Laplace's demon, knew the state of every particle, it could predict the entire future. Although quantum physics showed this deterministic dream was impossible, the mathematics he developed to pursue it, such as the Laplace transform, became the foundation of signal processing and control engineering. Every time your streaming service recommends a film or an autopilot system adjusts an aircraft's route, you're seeing an echo of Laplace's impossible dream. And so, we return to the crime scene. The mathematics they made us hate wasn't the problem. The problem was that we were never told the story, never shown that each equation was the solution to a human drama. Each symbol, a monument to a mind that dared question the impossible. The language of reality isn't cold. It's the score of the most beautiful symphony. It isn't a set of rules, but the very structure of reason, the grammar of the universe, and the beauty that hides behind everything. This is the story we came to tell. Mathematics isn't a prison. It's the grammar of the universe, the secret music behind everything. And this is just the first note. If this first page of the story sparked your curiosity, make sure you don't miss the next chapter. Subscribe and join us in this exploration. Mathematics gave us the language to describe the universe. But how do you ask the right question? How do you trust what your own eyes see? When millennia of wisdom say otherwise, the answer would give birth to a force even more powerful than calculus, the scientific method. Think in the void.